Hi everyone, my name is Patrick McCorry, and today I'm here to talk to you about validating bridges and rollups. But before we get to that, I work at the Arbitrum Foundation. I'm a researcher slash academic slash I like to do education, and historically I did my PhD in cryptocurrency, so I did that from 2013 to 2016. First on Bitcoin, then Ethereum. And as over the years, I've really worked on and studied blockchain scalability solutions like rollups. So hopefully I can give you an appreciation for why this technology is important, and you get a good mental model of roughly how it works and what problem it really solves. That's sort of what I want to get out of this. So let's jump ahead and get started. And the first question was, I normally ask this in person, but of course this is on videos, so I can't ask you, but I'll ask anyway. Okay, so raise your hand if you've ever used a cryptocurrency exchange like Binance, Coinbase, or Bitstamp. And most of the time, people raise their hand. There's quite a lot of people who've used these services by now. And the reason why I mention it is because when you think of a cryptocurrency exchange from a systems perspective, there's two things to highlight. One, it's fully custodial. They can freeze, they can confiscate, or they could just lose your funds. And we've seen several examples now of custodial systems losing customers' funds, not out of malice, just by incompetence as well, as we're going to see. The second one is that these systems are not auditable. They're opaque. You can't verify, you can't check their liabilities. You can't see if they're fully collateralized. You can't see if they're solvent. You just have to trust the word of the operator and maybe third-party audits, but that's a really hard thing to do in practice. And that sort of sucks for everyone involved. It sucks for the operator because it comes with risk. It also sucks for users because now you have to fully trust the operator to protect your funds. So this sort of brings us to the heart of all the interaction between the user and services like Coinbase and Binance and Kraken and FTX and just cryptocurrency exchanges in general. At the heart of all this interaction is really bridge engineering. All we're doing is going from one database, creating a bridge to another database, and moving the funds over, as we're going to see. We're just building bridges where the funds sit with the bridges, and they may release the funds at any time. Let's give a concrete example of that. So the first example is, let's say we're on Ethereum. We have this off-chain system called FTX, and there's a bridge. You can imagine this smart contract on Ethereum, the bridge has some functionality. I could deposit funds into the bridge, and maybe I could withdraw my funds from the bridge as well. Now let's pretend I already have funds on FTX, and let's say Alice has 1,000 ETH on FTX. If Alice wants to withdraw her funds, she'll have to poke FTX and say, FTX, please allow me to take my 1,000 ETH out of your system. In practice, what would happen is that FTX would sign a message to say, that basically attests to the fact that Alice can withdraw her 1,000 ETH. That would be sent to the smart contract. The smart contract holds all of the user's assets, all the assets locked in the FTX. It will receive a message from FTX to say, bridge, you may give Alice 1,000 ETH. Now, from the bridge's perspective, the bridge is holding all of these funds, and it should only release the funds if it's certain or if it's confident that the off-chain database is correct as well, all the funds are accounted for, all the liabilities are accounted for, and Alice indeed owns 1,000 ETH, and she's entitled to this 1,000 ETH. Now, in this example, because FTX has signed off on it, the bridge will trust FTX and, of course, give Alice her funds. Now, I'm sure some people have seen the FTX trial, which is probably a decent example of why you should not trust custodial exchanges. Maybe just put it that way. We shouldn't trust these custodial systems. And of course, Alice can then withdraw her 1,000 ETH. But generically speaking, what's happening here under the hood? Under the hood, you have the smart contract that lives on a blockchain network. It could be a set of addresses, it could be some code, but it holds all of the user's assets, all of the Bitcoin, all of the ETH that is locked into this off-chain system. And in the off-chain system, you have a database, it records account balances, maybe program state. When I log on Coinbase, I can see my account balance. That's really just reading a database. And this database records the liabilities. Who is owed what quantity of funds. What the bridge really wants to make sure is, we want to make sure the system's solvent. the bridge's assets can cover the liabilities in the off-chain system. And the bridge needs to be convinced that it is solvent, it can cover the liabilities before it allows users to withdraw their funds. And so as the trust assumption, how can the bridge be convinced that the off-chain database is correct, all the liabilities are accounted for before it releases funds back to the user? Now, the simple example is a single authority. Maybe the bridge will just trust the system's operator. It could be the Coinbase, the Bitstamp, or the FTXs. Maybe there's multiple authorities. Maybe you design a system to say, well, what if I trust 2 out of 3? Let's say Coinbase and Bitstamp and FTX. If 2 of them say that Alex can get 1,000 ETH, then maybe I just trust that word. That's sort of how RSK works. That's how Liquid works. K out of M parties. Now, there's these other type of bridges called crypto economic bridges. And as we're going to see, they're basically multi-authority bridges. You're still trusting maybe 5, 6, 8 parties. But the difference is that if I want to, I could stake my assets, I could put skin in the game and appoint myself to be one of those authorities. So that's how it works sort of in Polygon. So back in 2021, nearly 2 years ago now, the top 8 stakers, basically owned 85% of the stake locked in, as part of the process. And you have to trust these 6 entities to protect your funds in the Polygon proof of stake bridge. So it's still a multi-authority bridge, but it's better than one authority. And they have skin in the game. If the bridge gets hacked, their stake is probably going to 0. So that's why it's crypto economic in a sense. But in all 3 examples, we're still trusting less than 10 parties to protect our funds. And that sucks. And it doesn't suck from an ideological perspective. It sucks from a practical perspective. And that's because cryptocurrency exchanges over the years just keep getting hacked. Mt. Gox lost 6% of all Bitcoin. Binance lost, when was it? I think they lost, at the bottom there, they lost 7,000 Bitcoin because their hot wallet got hacked. Bitfinex had lost 120,000 Bitcoin in 2016. That recently got recovered thanks to the FBI. We can talk about that afterwards. But the problem here is that the problem with these custodial exchanges is not that they're malicious. These exchanges want to do the right thing. They want to be honest parties. They want to provide you a service. They want to protect your funds, and they want to earn a fee for doing that. But that is such a difficult job to do right, because you have to basically take a little single private key, I think 32 bytes or something, and this little digital file, if stolen, could lead to the loss of users' funds. So what these exchanges have to do is they have to hire people, implement a set of human processes to protect these private keys. And that's just, and if one company can get that right, that's good. But then every single company that comes along, every single system with a database that touches crypto assets, they need to re-implement these human processes to protect the funds. And humans aren't good at following rules. These human processes just don't work at scale, and that's why these companies keep getting hacked. And it just sucks for everyone, including honest parties. Like a lot of people doing startups today, they shouldn't need to take on the responsibility to protect billions of dollars. That's a huge overhead for a lot of companies. They just, it's a very terrifying thought to think about if you were put in that position. So we end up with like the Coinbases who've really done this well. And it's not really transparent, but you trust that they did it well. Now, the reason why I mention is because the whole point of rollups and validating bridges and everything we build in the blockchain world goes back to the initial idea of Satoshi Nakamoto and Bitcoin and what he was really gearing towards. And all I want to highlight is that the whole point of cryptocurrencies, or at least a better name for it, is trust engineering. We're just building systems where we can define, measure, and reduce or eliminate trust. That's the type of systems we're building. Can we remove trust out of the system? So instead of trusting humans to do the right thing, can we trust software and cryptography? And that's exactly what Satoshi said in his, I think it was one of his emails. What is needed is an electronic payment system based on cryptographic proof instead of human trust. And so this entire field is just about trust engineering. Again, define, measure, and eliminate trust. And that's all we're trying to do with these blockchain systems. So the question is, can we transact in an off-chain system while still allowing users to maintain self-custody of their funds? And historically speaking, that was one of the big ideas in 2014 with the sidechain paper by Blockstream. They don't use the word bridge in the paper because it's like 10 years ago now, but at the heart of the paper was the idea to build a trustless bridge. Could I take my Bitcoin, lock it up, unlock it on an experimental blockchain, transact away, and then bring my funds back? Unfortunately, it still wasn't a trustless system. And the issue was that if I take my Bitcoin, I lock it up in Bitcoin and unlock it somewhere else, if that blockchain goes offline, then my funds get stuck. So that sucks. So the real question is, can we build a bridge that will allow me to move assets to another off-chain system and still protect me from an all-powerful authority? Even if that system goes offline, could I still get my funds back out? And that sort of began with Plasma. Plasma was one of the first solutions to do this. There was this paper by Joseph Poon and Vitalik. I don't really recommend reading it now, just because it's very difficult to read. Joseph Poon made a joke to me that it was aspirational. But the idea in there was really awesome. So the idea was that you could lock the funds up of the smart contract, and even if the system goes offline, that doesn't matter because the smart contract holds your funds. And if it can detect that the system's offline, it will then allow users to withdraw their funds. But the problem with Plasma was that the design space wasn't very good. It was too confusing. It was 2 years of going around different, Plasma AVM, Plasma Leap, Plasma Prime. It was just very complicated until eventually Barry Whitehat came up with a repo called the Rollup, where he really just simplified the design space and made it much easier to design systems where, I could build a bridge, lock my funds up, put it on an off-chain system, and transact there. He basically solved the problem by posting all the data to Ethereum, but keeping the execution off-chain. And that led to the idea called a validating bridge. And the idea is fairly straightforward. You have this off-chain database that records all the liabilities. Then anyone could come along and try to provide an update to the database. So if an executor, they want to update the database with a list of transactions. But now the difference is the executor has to take that database update and propose it to the bridge smart contract and say, bridge, here's an update to the database. I can convince you that this is a valid update and all the balances are accounted for. The bridge will get the update and it'll say, well, executor, that's a great database update, but I don't trust you. So you have to provide me convincing evidence that this update to the database is indeed valid and correct. And the executor will have to provide convincing evidence, which could be a zero-knowledge proof, maybe as a fraud-proof system, an optimistic rollout, for example, but they have to provide cryptographic evidence that this is indeed correct. Then the smart contract will receive the evidence, it will check the evidence, it will validate the evidence, and it will be convinced that the update to the database is valid and correct. So that's cool, and that's all we're really doing. We're just periodically checking these database updates, and every single rollout project out there is trying to build that. And ultimately, if it works, then this smart contract living on Ethereum could protect your funds that are locked into an off-chain system, protect you from censorship, invalid transactions. Always guarantee that if the off-chain system goes offline for whatever reason, the customer and the user can always get their funds back out, and the user is safe and protected. So that sounds cool, but how do they work? So I just want to provide a high-level overview about the agents. Here's in the protocol, and then how does a validating bridge work? So there's 3 parties in a rollup or a validating bridge. You have a user, like Mooncats. You have the sequencer. It's a bit like the front end of the system. They take users' transactions and they'll decide the ordering of these transactions, and then they'll post it somewhere else. Then the executor will pick up the transactions, execute the transactions, and try to convince the bridge about its final execution. So again, we have a user, they deposit funds into the system, into the bridge, and it pops up on the off-chain system. Now, maybe Alice wants to send some coins to Bob. Hi, Bob. So Alice will sign a transaction and give it to the sequencer, and she'll transfer 1 coin to Bob. Now, what the sequencer can do is that the sequencer can notify Bob to say, Bob, you're going to receive 1 coin. But this transaction is currently pending. The sequencer has it, but it's not confirmed. It's not final. the sequencer will wait around for more pending transactions until eventually the sequencer has a big batch of transactions, and they'll basically post this directly to the bridge on Ethereum, or they'll pass it directly to the executors, depending on how the system's designed. But the idea is that they finalize the ordering and they pass it on. Now, the transactions are ordered, but they're not yet executed. So the executor can come along, pick up the transactions, and then they can execute it. You know, my 1990 animation, they'll execute the transactions, and then they'll post to the bridge to say, bridge, given those lists of transactions, this is what the database now looks like. Here's a checkpoint to say, this is exactly what the database looks like. You know, it's like a Merkle tree of all the values inside the database. You know, it's just a single commitment. And of course, they'll post convincing evidence. It could be a zero knowledge proof, maybe it's a fraud proof system, that this update is indeed correct beyond all reasonable doubt. And that's how these systems work. So you just have an off-chain database, and every time there's an update to the database, the smart contract has to be convinced that update is correct and valid before it will release any funds to the user. So it's always keeping track of every updated balance of the user or any activity happening on that off-chain system. And of course, any user can come along, pick up the list of transactions, execute it themselves, and get a copy of the database themselves as well. So what's the adversarial threat model? You know, what does it mean to be secure? What does it mean to defend against an adversary? So what we assume is that the user can always send a message to the bridge. And we assume the sequencer, or sorry, the adversary can corrupt every single party on the off-chain system. So we assume this entire off-chain system is corrupted. You know, any message sent on the off-chain system can be viewed, reordered, or dropped by the adversary. The entire system could be offline. That's what we're assuming. We just assume Alice can reliably send transactions to Ethereum and to the bridge smart contract on the blockchain as well. What we also assume is that the adversary can corrupt every single party, or nearly every single party, on the off-chain system. They can corrupt all the sequencers, all the executors, every other customer on the system. We just assume that the smart contract that lives on Ethereum, that bridge, is secure and honest. And we assume there's one honest party out there that can step up to protect the system. This could be Alice herself. And that's amazing. One honest party, anyone on the internet, can protect the integrity of this off-chain system. And that's probably the most powerful, or that's the most extreme threat model you can think of. Adversary can control the message flow, corrupt nearly every party, and yet the user can still protect their funds in the system. And hopefully we can deploy this, then we can actually protect users in real time and not have to rely on human processes. But is it worth it? Is it worth to deploy these type of systems? And I would argue yes. In the legacy world of Web 2, we have these exchanges and these crypto services, and the legacy financial system, there's no proof of solvency. You know, liabilities are recorded in private and brittle systems. Funds can be frozen. We're relying on humans to protect funds, not software or cryptography. Everything's closed source and there's no oversight. That's terrible for everyone involved. You know, we want our systems that give you proof of solvency by default, real-time audits. Users can always get their funds out if the system goes offline, and open participation. Anyone can protect these funds. And the future is really, the sequencers like the front end, the user experience, and the back end is that fraud proof, the zero knowledge proof, the executor. You just need one honest party out there to protect the system. That could be anyone. A swarm of cyber hornets, as long as there's one person out there willing to step up. And so what I like to see is this evolution. We're going from these custodial systems, there's the Coinbases and the FTXs and the Binances. I don't want to throw them all in together, but they all have the same system design. These public databases where maybe we can audit it, but the operator still controls it, to advance these open databases where anyone can read, write, and protect the database. Anyone can protect the database. That's the most important thing to consider for rollups. And that's what we're building today. So Arbitrum, Starkware, ZK Sync, Optimism, we're all in this open database category because we're there, and Polygon's also there now with their ZK EVM and Scroll. We're there to protect users and allow anyone to protect the system, just one honest party. And that's the world of Web 3. We're going away from this custodial world to this new world that looks quite similar. There's still this single off-chain database, but anyone can protect the system. We don't have to rely on a trusted system operator to protect the system. And I believe this is really exciting because custody is a liability for most off-chain systems. If I were to ask you to raise your hand, would you want to run a startup that had to protect $1 billion? Or would you want to have a startup where the tech stack protects $1 billion? Everyone will raise their hand for the tech stack. We want software and not humans to protect these users, folks. And so my belief is that it's very difficult to replicate human processes to secure billions of dollars. We've tried this for 14 years. It's very difficult to do. And so you just end up with 1 or 2 large companies that can achieve it. If one rollup team can get it right, hopefully Arbitrum can, that's why I work there. One team can get this right, and we can take this software stack, give it to all these companies, allow them to redeploy the tech stack, a bit like Linux, it's just a tech stack. Then maybe the software can protect the funds by default and not humans. Users don't really care about custody issues per se, but operators do. And that'll be what drives the adoption of rollups. Because operators do not want to protect billions of dollars if the software can do that for them. So this is the end of my talk. I hope you enjoyed it, and I hope you have a bit of a better understanding of why rollups are really, really exciting, and you should hopefully chat to us more about it.